In this video, we're going to talk about linear combinations and spanning sets. A set of two vectors forms a spanning set for R2 if every vector in R2 can be written as a linear combination of those two vectors. So, what does linear combination mean? This is what it means. If u, v, and w are vectors, and if w can be expressed as au plus bv, where a and b are scalars, real numbers, then w can be written as a linear combination of u and v. That is the linear combination right there, where a and b are both real numbers. So, for example, we know the vectors I and j span R2 because every vector in R2 can be written as a linear combination of I and j. So, for example, 4, -3 is 4i minus 3j. So that's a simple example. And if you're curious, can one of these numbers be 0? The answer is yes, that's allowable. So what we want to do now is show that the vector 423 can be written as a linear combination of the set of vectors -1, 4, 2, 5. So in other words, we want to show, if we can show that 423 can be written as a linear combination of -1, 4, and 2, 5, we'll be able to show that by doing some number of -1, 4, some multiple of that, and then following it up by some multiple of 2, 5, we'll be able to get to the vector 423. Notice how this is just a multiple of -1, 4, and how this right here is parallel to 2, 5. So we can see intuitively, yes, this is possible, but let's see if we can figure out what those scalars would be. So what we do is we let 423 be a linear combination of those two vectors. So in other words, we let 423 equal a times -1, 4 plus b times 2, 5. That would mean 4 is equal to -a plus 2b, and 23 is equal to 4a plus 5b. 4 is equal to a times -1 plus b times 2, and 23 is equal to a times 4 and plus b times 5. Okay? So what you see here, pretty simple, is two equations, two unknowns. So we're going to rearrange equation 1. Equation 1 said 4 equals -a plus 2b, down towards the bottom there. We'll rearrange it a bit, and we'll be able to say that a is 2b minus 4. That means 23 will be equal to 4 times 2b minus 4 plus 5b. Distributing the 4, we get 23 is 8b minus 16 plus 5b, or in other words, 39 is 13b, or in other words, b equals 3. Well, since a is 2b minus 4 and b is 3, that would mean a is 2, which would mean that 423 can be written as 2 times -1, 4 plus 3 times 2, 5. In other words, 423 is written as a linear combination of -1, 4 and 2, 5. And so what that means graphically is this. To get from 0, 0 to 423, we can do -1, 4 once, follow that journey up with a second one, and then do 3 journeys of 2, 5, and that will get us to where we want to go. Okay? So we have a therefore statement, therefore 423 can be written as a linear combination of -1, 4, 2, 5. Now, before we can do our next example, let's discuss the term spanning set. A spanning set of R2 exists if every vector in R2 can be written as a linear combination of the vectors in the set. So what we want to do now is show that the set of vectors 2, 3, -4, -6 is not a spanning set of R2. Well, if we draw 2, 3, and -4, -6, we get the graph shown. And perhaps intuitively we can see that following these two vectors continuously, we're never going to get off that red line. All we have to do is think of a vector that's not on that red line, and we'll be able to show that we cannot achieve that vector by only using 2, 3, and -4, -6, and multiples of it. So we can see by starting at the origin and traveling only in the directions dictated by those two vectors, we'll never get off of that same straight path. So all we really need to do is pick a vector not on that same straight path and show that it cannot be expressed as a linear combination of our two vectors. So we choose the vector -1, 4. Now, we could have chosen the vector 5, -1. We could have chosen the vector -6, 0. It really doesn't matter. We could have chosen any vector that's not on that straight path. We chose -1, 4 pretty randomly. So what we're going to do now, we're going to set up -1, 4 as a linear combination of 2, 3, and -4, 6, -6, and then show that it's mathematically impossible for that to happen. So we begin. -1, 4 equals a times 2, 3 plus b times -4, -6. Looking at the x's, we see -1 is a times 2 plus b times -4, and then we see 4 is a times 3 plus b times -6. And then we decide to use the process of elimination on our two equations, two unknowns. So we are going to multiply equation 1 by 3, and that'll give us a coefficient of 6 in front of the a. And we'll multiply equation 2 by 2, and that'll give us a coefficient of 6 in front of the a. When we do that, we get the equations shown, and then we recognize we have an opportunity to subtract. And if we subtract all three of these columns, we'll eliminate the a's. So we do that, and what we end up with is -3 minus 8, which is -11, will equal 6a minus 6a, which is 0a, and then -12b minus -12b, which is 0b. So we get -11 is 0a minus 0b, and if we were to factor out that 0, which isn't really, making sense, so to speak, but if we factored out that 0, ultimately we see -11 over 0 is equal to a minus b, and that's clearly not possible. There's no way to divide by 0. Another way of saying it, you don't even have to get that far. You just look at that equation and you know 0 times a is 0 automatically, and 0 times b is 0 automatically. So there's no way that that equation could come true. So since we came across a mathematical impossibility, there must have been a mistake earlier on, and what it is our initial supposition was wrong. The initial supposition was that we could express -1, 4 as a linear combination of 2, 3, and -4, -6. Since we cannot do that, that means there is a vector in R2 that can't be stated as a linear combination of 2, 3, and -4, -6. That means that set is not a spanning set of R2. Now, this next one's in blue. It's pretty sophisticated. It's actually, I think, really, really cool. We want to show that the set of vectors 2, 1, -3, -1 is a spanning set for R2. Now, it's not enough here just to pick a seemingly random vector and show that that vector can be expressed as a linear combination of these two. We have to show that the general vector xy can be expressed as a linear combination of those two with coefficients in front of each of those vectors that actually exist. So here's what it says. This is a tougher question than the last one. It is easier to prove that you can't say something is always true, i.e. by just finding a counterexample, than it is to prove that something is always true. Specifically, this question is asking us to show that no matter what vector from R2 we choose, it will be a linear combination of the vectors given. Well, we'll begin by letting xy be a vector in x2. In other words, we're saying the x and y are numbers that exist. Then we're going to state that xy is equal to a times 2, 1 plus b times -3, -1. And we'll show that a and b can each be expressed in terms of x and y. And since x and y both exist, then a and b will also both exist, and we will have made a valid statement. So let's get to work. And if we could do that, that would mean any random vector x, y, and R2 could be expressed as a linear combination of 2, 1, and -3, -1, meaning that 2, 1, -3, -1 was a spanning set for R2. So to begin, we write it as a linear combination. And then we say that means x must be a times 2 plus b times -3. and y must be a times 1 plus b times negative 1. Now from equation 2, we're going to rearrange a little bit, bring b to the other side. We'll say a is equal to b plus y. And then we'll take that expression for a and plug it into equation 1. And when we do that, we'll get, after distributing the 2, we'll get that x is equal to 2b plus 2y minus 3b. In other words, x is 2y minus b. We want to isolate b because we want to show that b is a number that exists. So we'll move b to the other side, move x to the other side, and we'll say b is equal to 2y minus x. Well, earlier on, we said xy is a point in R2. In other words, x and y both exist. And since x and y both exist, b, 2 times y minus x, is a number that exists. So we're halfway there. Now we're going to take that expression for b, which is 2y minus x. We're going to sub it into either equation 1 or equation 2. We choose equation 2 because they're our smaller coefficients. And so we say y is, instead of a minus b, we say a minus the quantity 2y minus x, which is like saying y equals a minus 2y plus x. In other words, we could say 3y minus x is equal to a, and now we've isolated for a. Now, since x and y both exist, that means a exists. And since a and b both exist, then that means we were able to express some random vector as a valid linear combination of those two vectors, 2, 1, and negative 3, negative 1, meaning the set of 2, 1, negative 3, negative 1 is a spanning set for R2. Now, just to show you what it was that we did, another way of saying what we did is to say that we found a formula for a and b that'll work given any vector in R2. So let's put that to use. Suppose we wanted to determine the coefficients in front of 2, 1, and negative 3, negative 1 that would work for the vector negative 7, 22. So what we'll do is we'll say negative 7, comma 22 is equal to a times 2, 1 plus b times negative 3, negative 1. X is equal to negative 7, b is equal to 22. So b is equal to 2y minus x, and a is equal to 3y minus x. That means b would be equal to 2 times 22 minus negative 7, ultimately 51. And a would be equal to 3 times 22 minus negative 7, ultimately 73. And so we'd be able to say that negative 722 is equal to 73 times 2, 1 plus 51 times negative 3, negative 1. Now, if you were to actually do the work like we did in the first example in this video and just put an A here and a B here and determine the values of A and B the way we did in that first example, you would get the same values, 73 for A and 51 for B. So in other words, that whole first part we did of this blue slide, of these blue slides, the first thing we did coming up with those expressions for A and B, what we were really doing was determining a formula for A and B no matter what values of X and Y you give, so long as they're real numbers and it's a vector in R2. Now, let's talk about terms to know. Two vectors are collinear vectors if they're parallel and lie on the same straight line. Now, you can tell algebraically if two vectors are collinear by determining whether they're scalar multiples of each other. So, for instance, these two vectors here, negative 3, 2, and 12, negative 8, are collinear because there's a factor of negative 4 there. Negative 3, 2, the vector times negative 4 will give you the other one. And similarly, these vectors here, 5, 15, negative 30, and 1, 3, negative 6 are collinear. But these vectors are not collinear, and neither are these. Okay? So, how does that relate to spanning sets? Well, any two non-zero, non-collinear vectors in R2 will span all of R2. And any two collinear vectors in R2 will not span R2. And that's consistent with the examples we did a while ago. And that's what it says at the bottom of that slide. Now, another Similar related general rule regarding spanning sets. Any two non-zero, non-collinear vectors in R3 will span a two-dimensional plane in R3. So any two non-zero, non-collinear vectors. So there will be many other vectors in R3 on that plane and many other vectors in R3 not on that plane. So as an example, think of the vectors I equals 1, 0, 0 and j equals 0, 1, 0. Those vectors are not collinear, but they span the entire plane consisting of vectors with a z component of 0. And later in the course, we'll do a lot of discussion about planes. So any two collinear vectors in R3 do not span a plane in R3. Now, let's do a couple of meat and potato type of examples here. Given the two vectors A equals -1, -2, 1, and B equals 3, -1, 1, we want to know if the vector -9, -4, 1 lies on the plane spanned by them. These are definitely not collinear vectors, and they're in 3 dimensions, so they will span a plane in R3. This vector here may be one of the other vectors on that plane, and it may not be. Let's figure it out. And here's the process. What we'll do is we'll assume for a moment that it does lie on the plane spanned by A and B. And what we'll do is we will say, since it lies on the plane spanned by A and B, we'll say that we can write that vector -9, -4, 1 as a linear combination of the other two vectors. Then what we'll do is we'll focus just on the x and y components. So focusing on the x component, we'll get -9 equals m times -1 plus n times 3. And focusing on the y components, we'll get -4 equals m times -2 plus n times -1. Okay, what we've got there at the bottom, what I've just circled here, is two equations, two unknowns. So we're just going to solve. So we'll rearrange equation 1, isolating m. We'll get m equals 3n plus 9. We'll sub that into equation 2. When we do that, we'll get -4 equals -2 times 3n plus 9 minus n. Ultimately, what we'll get is 7n equals -14, which means n will be -2. Now what we'll then do is we'll plug that expression for n into either equation 1 or equation 2. So we plugged it here into equation 1. And doing that, we get -9 equals -m plus 3 times -2. And so we get that m is equal to 3. Now, it's not much of a surprise, and it's not too illuminating at this point to have come up with a solution for m and n. That'll typically happen. But what we want to do now is see if those values work for the z component. In other words, we've got 1 equals m times 1 plus n times 1. Is that true if we let m be 3 and n be -2? Well, let's find out. Focusing on those z components, we get 1 equals m plus n. Again, 1 equals m times 1 plus n times 1. Using the values m equals 3 and n equals -2, let's see if we get a true statement. 1 equals 3 plus -2, and that's true. Since it's true to say that -9, -4, 1 is a linear combination of those two initial vectors, which means it lies on the plane spanned by them. Interesting. Well, wonder what it looks like if it doesn't work. Well, we're going to do very similar question, the same two initial vectors, and we're going to have C, instead of being -9, -4, 1, it'll be -9, -4, 2. The answer to this question will ultimately be no. So what we're going to do is follow the same procedure. We're going to let -9, -4, 2 equal m times -1, -2, 1 plus n times 3, -1, 1. We'll come up with an equation from our x components and an equation from our y components. We'll have two equations, two unknowns, just like we did a couple minutes ago. We'll rearrange one to solve for one of the variables, isolate one of the variables, and then we'll ultimately know that n is -2. We'll take that n value of -2, plug it into either one of the original equations, and we'll get that m is 3, just like we did a minute ago. And now we will test on the z components. Focusing on the z components, now we're testing 2 equals m times 1 plus n times 1. So we get 2 is m plus n. Well, m is 3 and n is negative 2. That's what we're testing. So we would get 2 is equal to 3 plus negative 2, but that's not true. That's a false statement. So in fact, 2 doesn't equal 3 plus negative 2. As written in red, it's correct. So since it's not true, they're not equal, and therefore we cannot write negative 9, negative 4, 2 as a linear combination of the two original vectors. So therefore it does not lie on the plane spanned by negative 1, negative 2, 1, and 3, negative 1, 1. So those two most recent examples with the very similar looking vectors, what they're kind of showing there is that if you've got the two non-collinear vectors in R3, you're going to have non-zero non-collinear. You're going to have a plane spanned. Some vectors will be on it, some other vectors won't be on it, and we now have a way of testing. Now, suppose I tell you that the vectors u and v span R2. We want to know what values of a and b make the statement au plus bv true, au equals bv true. Well, since u and v span R2, that means u and v are not collinear. Therefore, it's impossible for the vectors to be non-zero scalar multiples of each other. Therefore, the coefficient of u and the coefficient of v must both be 0. If either one of them is not 0, the other one can't possibly equal it, no matter what multiple is given, because it'll be in the wrong direction. So we must know that a is 0 and b is 0. So if we've got two non-collinear non-zero vectors, the only way au equals bv is if a is 0 and b is 0. Now imagine that the vectors 1, negative 1, 3, and 3, negative 2, 4, and 5, mn are coplanar. Let's determine three pairs of values for m and n for which that would be true. Well, since the vectors shown are coplanar, therefore we know there exist scalars such that 5mn is equal to a times 1, negative 1, 3 plus b times 3, negative 2, 4. Well, from the x components, we get 5 equals a plus 3b. From the y components, we get m equals negative a minus 2b. And from the z components, we get n equals 3a plus 4b. Now, we've got equation 1, equation 2, and equation 3. We have three equations with four unknowns. It's impossible to solve for any of these values without assigning a value to at least one of the variables given. We have more unknowns than equations. And this is like when you just learned how to graph lines. You were given an equation with both x and y, and the only way you could get ordered pairs for x and y was to substitute a real number value in for either x or y and solve for the other one. We typically did this making what are called tables of values. So what we're going to do, we're going to have to choose a value for one of the four unknowns and determine if we can get values for the others. We're going to do a little bit of algebra first. We're going to rearrange equation 1 to get a equals 5 minus 3b. And now, if we do that, we're going to sub that into equation 2. And we're going to get m is equal to b minus 5. And we're going to sub that into equation 3. And we're going to get n is equal to 15 minus 5b. Okay? Now, in summary, we'll get a is 5 minus 3b, m is b minus 5, and n is 15 minus 5b. Well, we don't need equation 4 anymore, right here. Focusing just on equation 5 and 6, we have two equations with three unknowns. We need to assign a value to one of them and then solve for the other two. So since both of those equations are in terms of b, we're going to pick three possible values for b and then determine appropriate values for m and for n. So if we let b equal 1, then we'll see that m is negative 4 and n is 10. If we let b equal 2, we'll see that m is negative 3 and n is 5. And if we let b equal 3, we'll see m is negative 2 and n is 0. So the three vectors given are coplanar if m is negative 4 and n is 10, or if m is negative 3 and n is 5, or if m is negative 2 and n is 0. but there are many other possible pairs of values as well. Another way of doing the same question is to look at these three equations and say, okay, I've got equation 1 in terms of 2 variables, I've got equation 2 in terms of 3 variables, and I've got equation 3 in terms of 3 variables. Let's pick the simplest of those, which is equation 1. And then what we can do is simply looking at equation 1, we can simply make a little table of values. And we can say, okay, if I let b equal 1, then 5 will equal a plus 3 times 1, which would mean a will have to equal 2. If I let b equal 2, then 5 will equal a plus 3 times 2, which will mean a have to be negative 1. And if I let b equal 3, then 5 will equal a plus 3 times 3, which will ultimately mean a is negative 4. So what I will have just done is come up with ordered pairs for a and b. Then I can look at the situation where a is 2 and b is 1, and I can sub that in for m and n. So if I let a be 2 and b be 1, I'll get that m is equal to negative 4. But if I let a be 2 and b be 1, I'll get n is equal to positive 10. And that would be another way of getting to the same place. If that wasn't too clear, we'll do one more. We can go to the second thing, and I could say to you, what if I let a be negative 1 and b be 2? Well, if I let a be negative 1 and b be 2, then m would be negative 1 minus 2 times 2, which would be negative 3, but n would be 3 times negative 1 plus 4 times 2, which would be 5. And that would be another possibility. So you see here that there's a couple of different ways of going about that solution.